Hello everyone, my name is Daniel Wynn, and today's material is on the packaging of memory devices and the challenges that come with them. This content is brought to you by work done in the Security Assurance Lab at the University of Florida, under the supervision of Aslam Khan, Litin Kumar Biswas, and Dr. Naveed Asadi. The material for this video will be focused on memory devices and their packaging, and will be outlined by the following topics: general overview of memory devices, the differences between volatile and non-volatile memory, the different types of memory and their applications, current packaging methods of these memory devices, and future explored packaging methods such as wafer bonding. And then we'll move on to certain types of current memory types such as high bandwidth memory. And the video will close off with potential vulnerabilities of memory devices and their security mechanisms. First off, I'll be discussing about a general overview of memory devices. Memory devices are essential components in computers and electronic devices that store and retrieve data. These devices rely on semiconductor-based memory chips, which come in two main distinguishing types: volatile memory, that temporarily stores data while the device is on, and non-volatile memory, that retains data even when the device is powered off. Like everything else in this electronic world, a noticeable trend in memory packaging is the ongoing effort to reduce the size of these devices. Engineers and manufacturers aim to make memory devices more compact while maintaining the performance, leading to more efficient use of space and the creation of sleeker and more powerful electronic devices. In the image shown below is an example of volatile memory in the form of DDR4 RAM. Speaking about volatile memory, it is one of two categories that different types of memory is grouped into, the other being non-volatile memory. Volatile memory, commonly known as RAM, which is random access memory, is a temporary storage solution that allows computers to read and write data quickly during their operation. However, a significant characteristic of RAM is that it loses its contents whenever the power is turned off, making it unsuitable for permanent storage. On the other hand, non-volatile memory, such as ROM, read-only memory, and flash memory, serves as a reliable solution, which as they retain data without even a power source being on. ROM, as the name suggests, is read-only, meaning that the data stored on it cannot be edited or modified. Both memory types are crucial for the seamless functioning of computers and electronic, each serving specific purposes in managing data efficiently. The figure shown on the bottom right is a freeze frame of the simulated differences between RAM and ROM animated. When animated, the RAM figure slowly fills up with data, lighting up every orange square, while ROM is consistently fully lit up. After going more in depth with the types of memory as shown in this brief organizational chart, a few general memory types that fall within the volatile memory are DRAM, SRAM, and SDRAM memory. As for non-volatile memory types, the types of memories discussed today will be PROM memory, flash memory, EEPROM memory, and NAND memory. And while there are more different types of memory, these types of memory are some of the most distinguishable and commonly found. Moving forward are the companies within the semiconductor and electronic industry that are creating memory devices and or packaging memory devices. Samsung Electronics, SK Hynix, Micron Technology, Intel Corporation, and Toshiba Memory, which is now merged with Kioxia, are some of the main players in memory device packaging and fabrication in the semiconductor industry. All of these countries, while mainly based in other countries such as South Korea, the United States, and Japan, has a lot of its manufacturing outsourced to other countries, with China being the main force in production outsourcing. Samsung Electronics in particular, while they help package and create DRAM and NAND devices, have manufacturing plants in South Korea, the United States, and China. SK Hynix, which is also a South Korean-based company like Samsung, has a large portion of their manufacturing. Micron Technology, which is one of the US's main stakeholders in DRAM and NAND production, have their main manufacturing in the United States, Singapore, and Japan, but they but Micron also has partnerships with foundries and test contractors located in Taiwan and China. Intel, another US-based company, has most of its manufacturing outsourced to countries like Costa Rica, Vietnam, and Malaysia, as its United States, Israeli, Irish, and Chinese locations focus on design and development. And Toshiba Memory, which is as previously stated, now known as Kioxia, has their main manufacturing facilities in Japan and Taiwan, but they outsource to other countries as well for production. Outsourcing itself is typically used for cost-saving measures, while it also allows these companies that are outsourcing to focus on more specialized expertise while also mitigating risks and increasing their global market share. The main types of volatile memory that the previously stated companies tend to produce are DRAM, SRAM, and SDRAM. In order, the acronyms stand for Dynamic Random Access Memory, Static Random Access Memory, and Synchronous Dynamic Random Access Memory. DRAM, SRAM, and SDRAM are most commonly found in computers and other electronic devices for temporary data storage. They can also be found in networking devices and routers. DRAM specifically is one of the most commonly found memory types that are bought and used by consumers. Currently, volatile memory's packaging methods are usually dual inline memory modules, which is also known as DIMM. And the main body of DIMM is a printed circuit board, which is made up of fiberglass and reinforced epoxy composite. And DIMMs usually have multiple memory chips, which consist of semiconductor materials like silicon. And the main metals used in DIMM are aluminum, and they're typically used for heat dissipation, and gold, on the other hand, is used for electric conductivity. And as the future of packaging gets closer, DRAM is one of the most common memory types that are being looked into utilizing wafer-based packaging. Moving on to non-volatile memory, programmable read-only memory, which is also known as PROM, erasable programmable read-only memory, which is known as EPROM, flash memory, and NOT-AND memory, which is known as NAND memory, are currently highlighted. Non-volatile memory has high significance in storing and sending data, such as BIOS, firmware, and computers, and calibration data, and also portable storage. Currently, PROM and EPROM are specifically commonly packaged using the dual inline package, also known as DIP format, which features 2 rows of pins that plug into a socket on the circuit board. The DIP packaging offers a straightforward and widely used method for integrating the PROM and EPROM into electronic devices. On the other hand, other non-volatile memory devices such as flash and NAND memory are typically built on a single chip, as they are used for portable storage. And like many of the other volatile memory types, future packaging methods are being discussed with non-volatile memory as well, and they are also wafer-based packaging methods and hybrid integration. Wafer packaging involves mounting chips directly on a single wafer, which also introduces its own material challenges and opportunities in terms of miniaturization, interconnects, and heat dissipation. As stated previously, current package techniques are typically based on the die attach process, which is attaching an integrated circuit to a substrate or a lead frame, often made up of composite or ceramic. In the die attach process, epoxy is used as a bonding agent for the die and the substrate. Often, the die is once the die is attached, wire bonding is then performed, where the thin wires made up of conductive metals such as gold or aluminum are connected from the bond pads of the die to the appropriate connection points on the substrate or lead frame, establishing an electrical connection between the die and external package leads. In some other cases, an epoxy underfill is then used to fill the gaps around the die to minimize stress of the solder joints. And at the end of the die attach process, everything is then enveloped by an epoxy mold compound encapsulation, which The encapsulation protects the integrated circuit from environmental factors and external mechanical damage that could be found. Wafer bonding is seen as one of the grand methods that will be the key to advancing current packaging methods in the future. Wafer-to-wafer hybrid bonding is introduced to overcome scaling limit and eliminating old manufacturing challenges. The bonding process in this wafer-to-wafer hybrid bonding involves the copper metals from two different wafers being bonded together to form a single component, which allows for a smaller and more dense dies with increased data transfer rates. The bonding process is divided into three main steps, which are wafer processing, pre-bonding, and annealing. Processing the wafer requires the product to be clean, flat, and smooth on the surface itself of the wafer to prevent defects such as voids or internal bubbles. In pre-bonding, satisfactory electrical contact between the soon-to-be combined wafer done with precise alignment and accuracy. Any mismatch can result in lower yield rates, as shown in the first figure, where the hybrid bond is mismatched between the copper portions of the wafers. The aligning of the copper parts of the wafers then create a strong chemical bond through annealing of the copper until they expand and merge together as one unit. A challenge of the current packaging of current packaging of memory devices are needing higher memory storage per wafer by increasing layers. Current manufacturing methods, however, are resulting in lower yields, where wafer-to-wafer hybrid bonding can be the solution, as shown in the figure on the right. In this figure, this is a layer string stacking designed by Kioxia, where each stack could be integrated in an individual wafer. In enhanced wafer-level packaging, they had the highest potential for high performance while keeping the low cost. The first figure shown on the far left is a cross-section of a double elastomer wafer-level package assembly on an FR4 substrate. And as shown in the figure, the FR4 substrate is bonded to the solder through the metallic UBM, which is underbump metallization, which is then bonded to the compliant layers. These compliant elastomer layers can improve solder joint reliability. The middle figure summarizes the process flow of manufacturing this wafer level packaging. The process first begins with the sputtering of titanium aluminum, followed by a spin coat of the first compliant elastomer layer. The second compliant layer is then printed, followed by the sputtering of titanium, copper, and then electroplating of nickel with gold on it to construct a redistribution metal trace. A polyimide passivation layer is then spin coated on to protect the metal trace and defines the solder ball pad that is printed on. Next, after that, there's reflow and flux cleaning, and the process is ended with a die saw and assembly. Then the final figure on the far right, it shows a cross section with the sputter titanium, copper, nickel, and golden redistribution line and UBM between the elastomer layers and the solder ball. The resulting outcome of this is sputtering method is as a result of a previous failure where corrosion was found around the solder pad edges. Furthermore, with future concepts for memory devices is high bandwidth memory, also known as HBM. HBM is a recently developed memory type that focuses on increased bandwidth while also reducing overall power consumption of the device. HBM's main application outlooks are its usage in future graphics cards, artificial intelligence, and high-performance computing. HBM uses a 3D stacked architecture model as shown in the figure below. The 3D stacked architecture focuses on using through silicon via, also known as TSV, technology as its main technique. Traditional memory technologies, chips are placed side by side and data is moved through the traces connected between the chips. However, in the 3D stacked architecture, the dies are connected to one another using the TSVs vertically. And using this technology, it can work capacitance with a smaller area used and uses a lot lower power consumption compared to before. And SK Hynix is the first company that introduced this technology with a partnership they did with AMD in 2015. And the HBM device was first used commercially on AMD's Radeon R9 Fury series graphics. The newest generation in this line of memory devices is the High Bandwidth Memory 3, also known as HBM3. While HBM3 has a 3 after it is actually a 4th generation model following HBM, HBM2, and HBM2E. Currently, the HBM market is led by SK Hynix with 50% of its share power, which is then followed by Samsung Electronics with 40% of HBM share power, and Micron with 10%, and then ends off with Micron with 10% of the overall share market for HBMs. And although SK Hynix was the first commercialized creator of HBM, they have completely changed their technology packaging techniques used in HBM3 compared to the previous generations. They have superseded their previous models with a new one that utilizes a mass reflow molded underfill, also known as MRMUF, compared to the previous methods of TSV. The MRMUF packaging method uses an epoxy molding compound that fills the space between the chips, which allows for an increase of 50% memory while maintaining thickness of the chip. To increase capacity, chips are typically made thinner at the cost of it being easily bent, but the epoxy molding compound prevents that and keeps it nice and rigid. Micron, on the other hand, has developed their own HBM3 device and created another generation for it, where this memory device uses a 1 beta node rather than the original 1 alpha node that Micron used to use for their HBMs. The 1 beta node is created through means of advanced lithography and nanomanufacturing, and it increases the capacity of the memory by 35% while also reducing power consumption by 15%. And you can see Micron's a diagram of Micron's 2nd gen HBM3 in the figure shown. With artificial intelligence flooding the technology market, hardware is typically impeding the advancement of AI, or at least the capability to execute it. And more specifically, memory bandwidth itself is the bottleneck for AI. And because of this, development of memory types like HBM3 is critical to the growing market. In the current age of technology, the Internet of Things encompasses everything everywhere. And as per research of IBM, by 2025, more than 75 billion IoT devices will be connected in the world. With IoT devices being ubiquitous around the world, the concern with their cybersecurity and possible vulnerabilities arise. And within all of these IoT devices, memory is a crucial component within them that makes them a heavy target for vulnerability attacks. And these vulnerability attacks range from hardware attacks, software attacks, and data-related attacks. And as shown in the figure headed by Cisco's research, a vulnerability pyramid was designed based on the capacity for hardware or software to handle cyber attack in an Internet of Things system. And as shown in this figure, memory and data storage is at pretty high vulnerability. And an example of vulnerability in memory is DRAM hammering. DRAMs are highly susceptible to an attack called a row hammer attack, and in the end exploits DRAM single capacitor leak. Some security mechanisms to combat memory vulnerabilities in IoT systems are hardware-based. And one of these methods is using hardware-based authentication to allow user access to the memory. And the figure on the left showcases a basic procedure of the user authentication process for this. Step 1, the user buys a device that has this security mechanism installed on it already. And so when they buy the device from the vendor, they receive a user identification code from the vendor as well. And then for steps 2 and 3, the user signs in with the ID that they got, which then the information that the ID has been signed into gets sent back to the vendor, who verifies the ID and then sends back the authentication key to the user. And the final step of the user authentication process is that if the user enters both the ID and user authentication key, then it allows for access into the device, memory device. And the figure on the right showcases a hardware security mechanism called Secure Region Access Model, which secures specific data in specific regions in the memory. And so each protocol step needs to be followed correctly in order to unlock all portions or the portions that you want of the memory, or else those regions will be locked out to you. Here's the glossary. Here are the references.